Hello, class. Elon Musk is now the richest person in the world, surpassing Jeff Bezos. I don't think that'll last. How would it make sense that someone who owns a car company and a space company that doesn't seem as critical. I think his Tesla stock is just out of control, isn't the Tesla stock price? Just like way probably overvalued, in my opinion. I should short Tesla. You guys know what shorting is? It means you're basically betting against the stock price going up. Oh my gosh, I'm in a fart chamber today. I have both dogs right next to me, farting constantly, and a skunk sprayed outside last night. So it's just like, it smells horrible. I don't understand that question. How long do I think the Tesla Roadster will last in space? Probably billions of years. I don't see what would. Um, okay, so I'm going to go ahead and get started. Let me switch to my document camera. So the first thing I wanted to talk about today is I wanted to talk about how simple harmonic motion must occur about an equilibrium point. And when I say an equilibrium point, I mean a point where the force is zero. Okay? If you think about things that are oscillating back and forth, okay, you are not going to get something oscillating back and forth unless it's near its equilibrium. Like, what if you had something on a hill and you nudged it? If it's on a hill is not an equilibrium. So it's just going to roll down the hill and it's going to never come back. So the only way that it keeps coming back to where it started is if it's oscillating about an equilibrium position. Okay. So what if I have Newton's second law, net force equals ma, and what if the net force is minus k x minus c? So where is the equilibrium in this case? Where is the spot where, what is the x value? What is the x value where the force equals zero? Type it into the chat if you know. What is the x value where the force is equal to zero? Yeah, so if x equals c, the force is equal to zero. So x equals c is the equilibrium, okay? So it actually turns out that the equation minus omega squared x is equal to a, that is the equation of simple harmonic motion, but also an equivalent equation of simple harmonic motion is minus omega squared times the quantity x minus c equals the acceleration. So this equation has the general solution. This top equation has the general solution. X of t equals a cosine of omega t plus phi. All right. This other equation has a solution, a cosine of omega t plus phi plus the constant. Okay, so so the constant basically shifts the graph up or down so that it's oscillating about the equilibrium point. So if the equilibrium point is 0, your position time graph is going to look like this. So you're oscillating about x equals 0. But if your equilibrium point is at a different location, maybe x equals c, then it's still going to look like a sine or a cosine, but it's just going to be shifted up to reflect the location of the equilibrium. So you always execute simple harmonic motion about an equilibrium point, wherever that equilibrium is. Okay? So that's the first point in today's lesson. And we simply add a constant to the solution to get the new equilibrium. The second thing I wanted to talk about today is the ubiquity of SHM. So ubiquitous is a word that means you find it everywhere. Okay? Simple harmonic motion is everywhere in physics. So it's one of the most important things to study in physics, simple harmonic motion, because you see it so often. And so what I would like to attempt to answer is why. Why is it that we see simple harmonic motion everywhere? Okay? And so to understand why, we have to think about potential energy graphs. We talked about those graphs of potential energy versus position. All right? So what if I just have a random potential energy graph that, I don't know, does all kinds of stuff? Doesn't really matter what it looks like. Okay? This potential energy graph has 4 stable equilibria. Here, 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 and here. Okay? And what I want to do, all right, what I want to do is I want you to notice that near each equilibrium, the potential kind of looks like a parabola. All right? If we look at this minimum, it kind of looks like a parabola. Right? Doesn't that look like a parabola? This kind of looks like a parabola. All right? This kind of looks like a parabola. This kind of looks like a parabola. And it's only, so if we are at the minimum or close to the minimum, close to the equilibrium, it looks like a parabola. And the further we move away from the equilibrium, the more it deviates from the parabola. But near an equilibrium, the potential energy function is approximately a parabola. Okay? It's approximately a parabola. Now, I'm going to tell you I'm going to show you what that approximation is. All right. I'm going to show you what that approximation is, and why this is the approximation. Don't worry about it, because it's kind of math that you probably haven't been exposed to yet. But I'm going to focus on this equilibrium. So let's consider the equilibrium at x equals 0. So let's consider that equilibrium. Near x equals 0, we can approximate u of x is equal to u evaluated at 0 plus u prime evaluated at 0 times x plus 1/2 u prime prime of 0 times x squared. So this is an approximation. But see how it has x squared, so it's a parabola. All right? So this is the parabolic approximation. And in order to get the parabolic approximation, you need the value, the derivative, and the second derivative at the equilibrium point. Okay? So this is called the Taylor series. If you're in advanced math, it's called the Taylor series. Keeping in mind that to get the force function, we do minus the derivative. What is going to be this derivative evaluated at the equilibrium point? By definition of being an equilibrium point, what is the derivative? Type it in the chat if you know. Zero. Yeah, exactly right. So this is 0 by definition of an equilibrium. Okay. So what that means is that near an equilibrium, u of x is approximately equal to u evaluated at 0 plus 1/2 u prime prime of 0 times x squared. Okay. Flip the page. So we have near equilibrium, u of x is approximately u of 0 plus 1/2 u prime prime of 0 times x squared. Okay, so now we can calculate the force near equilibrium. So near equilibrium, the force as a function of position is going to be minus the derivative of the potential. Okay, so when I take the derivative of this, it's a constant, and then I have a constant times x squared. So taking the derivative of x squared gives 2x. All right. So what we get is that the force is going to be minus u prime prime of 0 times x. That's only near the equilibrium, but yeah. Okay. Then near equilibrium, Newton's second law becomes net force, which is this, minus u prime prime of 0 times x, equals ma. So that is Newton's second law near the equilibrium. Okay? So dividing both sides by m, I get u prime prime over 0 over m times x equals a. So now I want to compare that with the defining equation of simple harmonic motion, which is minus omega squared times x equals a. So who can tell me from this comparison, what is omega squared equal to? By comparison, so we have A here, we have X here, we have minus sign here. So what's omega squared equal to? Okay, so what's minus A over X in this equation? Solve it for minus A over X. U prime prime of 0 over M. Excellent. U prime prime over M. So that means that omega, okay, is square root of U prime prime over M, okay, which means that the period is 2 pi over omega, which is 2 pi times the square root of M over U prime prime, evaluated at equilibrium. And so that is the period. Okay? And I changed it because we were considering the equilibrium at x equals 0. So we were evaluating U prime prime at 0, but in general, if you have an equilibrium that is not at x equals 0, this would end up being U prime prime evaluated at that equilibrium point. So, what have we shown here? We have shown that near an equilibrium, okay, near an equilibrium, Newton's second law has the form, has the simple harmonic motion form. Okay? So, as long as the particle doesn't go far from equilibrium, it will undergo SHM. So that is why we see SHM everywhere. It's because things that are in equilibrium, if you disturb them, and it's a small disturbance, like not enough to completely destroy the object or change its configuration, if it's a small disturbance, then it's going to undergo simple harmonic motion, no matter what the shape of the potential is overall, okay? And the period of that simple harmonic motion is going to be that. Now, here is the general solution for simple harmonic motion. What parameter here determines how far you go from equilibrium? Okay? What determines the size of these swings? How far you go from equilibrium? Type it in the chat if you know. And so I'll give you an analogy. So if you had a ball rolling back and forth, okay, if the ball is rolling back and forth, and it's rolling back and forth not with a lot of swinging, just like small oscillation back and forth, then it's just going to stay in this valley, and it's going to undergo simple harmonic motion. But if the swinging gets too large, it could roll into this other valley and undergo a more complicated motion. Okay? Excellent. So the amplitude has to be small. So the amplitude determines how far from equilibrium you go. So that means that the amplitude must be small. Okay? And I'm putting that in quotation marks because really how small the amplitude needs to be depends on how close to simple harmonic motion you need the motion to look like. Okay? So it's kind of a sliding scale. So let's do an example. What if we have a potential that is given by maybe 7e to the 3x plus 4e to the minus 2x. Okay? So this is some weird potential. Okay? So if we think about it, 7e to the 3x, that's like an exponential growth. So it's going to look like that. E to the minus 2x is exponential decay. That's going to look like that. So if we add these two potentials together, we're going to get something that looks like this. Hang on a second. What to do, Hazel? Thought Hazel was getting in trouble. Okay, so we're going to have a stable equilibrium like right around here, close to 0. Okay, so what we want to do is find the period of small oscillation of a 1 kilogram particle in this potential. Okay, so the first thing you need to do is you need to figure out, well, gee, where is the equilibrium? So the first step is we need to find the equilibrium. And we find the equilibrium by setting the derivative of the potential equal to 0. Okay, so I'm assuming you know how to take the derivative of the exponential function. So u prime is going to be 21 e to the 3x minus 8 e to the minus 2x. And I set that equal to 0. So that says 21 e to the 3x equals 8 e to the minus 2x, which says that 8 over 21 equals e to the 5x, which says that the x value of the equilibrium is 1/5 natural log of 8 over 21. All right, so let me compute that. So that tells me that the equilibrium is at x equals minus 0.19. Okay, x equals minus 0.19 meters. So now what I want to do, so step 2, is I want to evaluate u prime prime at the equilibrium point. Okay, so now I need to do one more derivative of this. So that's going to give me 63 e to the 3x plus 16 e to the minus 2x. Okay, That's u prime prime. Now I need to evaluate u prime prime of negative 0.19 because that's where the equilibrium is. So that's going to be equal to 63 e to the 3 times 0.9 plus 16 e to the 2 times 0.19. Okay, so plug that into my calculator. And I get that that is equal to 59. Okay? So now the third step is I want to use the formula for the period in terms of the second derivative of the potential. So now I have period equals 2 pi square root of m, which is 1, over u prime prime at equilibrium, which is 59. And that gives a period of 0.82 seconds. So that would be the period of small oscillation. All right. So there you have it. So that's my lesson.